In the last days of October 2025, a faint dot near the sun begins to misbehave. On computer screens in solar observatories around the world, coronagraph images update frame by frame. The blinding disk of the sun is blocked out, and just beyond that artificial eclipse, a small, ghostly smudge glows blue-green. It has a catalog name, a predicted path, an expected brightness. But as it sweeps through perihelion at about 1.36 astronomical units from the sun, the equations that describe its light stop working. It brightens too fast. Not in a smooth, gentle curve, but in sudden steps, as if something deep inside the nucleus is waking up in pulses. Soho records the surge. Stereo A confirms it from another angle. Newer missions, Punch, Goes 19, watch the same thing. A gas-rich coma expanding, brightening, taking on that characteristic cyan tint of carbon and cyanogen, yet rising far above what standard comet models had forecast weeks before. On log-scaled plots of magnitude versus time, the smooth model curves lie in one place, calm and predictable. The real data points march upward on a steeper slope, then begin to oscillate. Every 16.16 hours, the light curve shows a small but sharp pulse, like a heartbeat. Deep in that glow, rotating jets on the nucleus sweep around in and out of view, each rotation briefly turning a more active face toward the sun and toward us. What should be a gentle, diffuse smear of dust and gas becomes something more like a signal, a regular flicker etched into the noise. The first puzzle grows quietly in the background of these plots. The comet's path is not exactly where pure gravity says it should be. Fit the astrometry with a simple Keplerian trajectory, and you see residuals. Small, persistent deviations. Add in the standard non-gravitational terms, the push from asymmetric outgassing, and it improves, but not perfectly. The measured gas production rates, the changing geometry of the tail, the direction and magnitude of the extra acceleration, they do not quite line up. Somewhere between the equations and the images, something is missing, or at least not yet fully understood. Only after this mismatch appears do we step back and reveal what kind of object is misbehaving. This is not a long-period comet, returning after millions of years. It is not a fragment from our Kuiper belt, perturbed inward by Neptune. Its orbit has an eccentricity of more than 6. Its velocity, even far from the sun, remains tens of kilometers per second. It is on a hyperbolic path that will never close. This is 3 Atlas, the third confirmed interstellar visitor. It is moving through the inner solar system at over 130,000 miles per hour, tracing a one-time path past our star, a brief crossing of gravitational domains before it is gone forever into the dark between suns. The question that hangs over every new data point is simple and unsettling. Why did this interstellar comet flare the way it did? And what, if anything, does that tell us about the star system it came from? If you enjoy this unfolding mystery, subscribe for more silent astronomer cosmic documentaries. To understand how strange its behavior is, we need to slow down and rewind the timeline. Months before the perihelion surge, 3 Atlas existed only as a few faint streaks on archived images. Recovery frames from May 2025 show a barely detectable speck just above the noise level of the sky. At the time, it is nothing more than one more anonymous moving point among countless main belt asteroids and distant comets. On July 1, 2025, the Atlas Survey Telescope in Chile flags a new object, C2025, non-Atlas. Its motion is fast, its brightness modest but promising. As more observations are added, orbital solutions begin to sharpen. At first, astronomers assume it is a long-period comet from the Oort cloud, falling inward on a vast, stretched ellipse. That is what experience says it should be. Then the numbers settle into place. The eccentricity climbs above 1 dot, then well above. The best fit value hovers around 6.14. The velocity at infinity, its speed far from the sun's pull, comes out near 57 kilometers per second. No closed orbit can describe it. Instead of belonging to our solar system, it is simply passing through. With that realization, the designation changes. C2025, None becomes 3 Atlas, the third I-class object, after Onai no Muamua in 2017 and Tue Borisov in 2019. The catalog code quietly rewrites its history. It did not begin its journey in the distant shell of icy bodies surrounding our system. It began somewhere outside, among the planets of another sun. Its path through our neighborhood is both strange and almost eerily aligned. 3 Atlas follows a retrograde orbit, tilted by about 175 degrees to the ecliptic. It is moving opposite the direction of the planets, yet the plane of its trajectory lies nearly in the same flat disk that contains Earth, Mars, and Jupiter. It skims through our gravitational architecture, like a grain of dust passing through a spinning vinyl record, cutting across the grooves at a slight angle. Perihelion comes on October 29, 2025. At a distance of roughly 1.356 astronomical units, just beyond Earth's orbit. Before that, in early October, it slides within 0.119 of Mars, close enough that the red planet's fleet of orbiters can turn their instruments toward it. In early November, it passes about 0.650 from Venus. On December 19, it reaches its minimum distance from Earth, about 1.80. No threat, no close pass in the dramatic sense, but close enough for our telescopes to watch it fade in exquisite detail. Months later, on March 16, 2026, it will have a closest approach of about 0.360 to Jupiter, one last gravitational conversation, before it leaves the planetary region behind. Set against human timescales, this sequence feels long. Months of tracking, years of modeling. Against the object's true journey, it is nothing. Dynamical studies suggest that 3I Atlas may have wandered through interstellar space for billions of years before this brief encounter, ejected from its birth system by some ancient rearrangement of planets. Each photon we collect from its coma is, in a sense, a sample from another planetary nursery. A distant disk of gas and dust that once circled an unknown star. Once its interstellar nature is confirmed, the response from our observing infrastructure is almost automatic. The modern sky is watched by a distributed overlapping network of instruments, and now many of them turn toward a single, faint, moving target. NASA coordinates a broad campaign. Hubble is allocated time in July to catch the object while it is still inbound, and again near the end of November when the effects of perihelion heating are in full force. JWST schedules near-spec observations and August peering at the infrared glow of dust and ISIS. TESS and other survey missions incorporate targeted scans into their broader sky coverage, building time series photometry that tracks the comet's subtle flicker. SWIFT, with its ultraviolet instruments, looks not for the comet itself but for the products of water broken apart by sunlight. Hydroxyl radicals that fluoresce in UV wavelengths, a proxy for the invisible stream of HEO molecules leaving the nucleus. SPHERIX prepares to map its spectra across wider swaths of the sky. Even missions not designed for comet science, Parker's Solar Probe, SOHO Punch, had 3I Atlas to their watch lists, each from a different vantage point in the inner system.
Look at how beautiful
Elsewhere,
the universe
Bodic
is.
explorers join in.
So many stars,
The Perseverance
so
rover's
many
sky cameras
possibilities
on
out
Mars, the Mars Reconnaissance Orbiter, MAVEN and ESA's ExoMars Trace Gas Orbiter all have opportunities at different times to try to catch the dim visitor as it moves through Mars' portion of the sky. Further out, missions like Europa Clipper, Lucy, and Psyche carry instruments that can, if geometry and mission priorities allow, contribute occasional measurements, adding more perspectives to the growing data mosaic. On the ground, the response is equally broad. The Very Large Telescope in Chile, Pan-STARRS in Hawaii, Subaru in Mauna Kea, and dozens of other professional observatories fold 3E Atlas into their schedules. Their images capture the evolving shape of its coma and tail, trace the angle of its anti-tail, and resolve, just barely, the structure of jets fanning out from the unseen nucleus. Amateur astronomers, scattered across longitudes, stack hundreds of FITS frames from small backyard telescopes, using software to tease out a light curve from the noise of the sky. Their dense, continuous data help refine the rotation period. The 16.16-hour heartbeat becomes more certain with each added night. Together, this worldwide network builds a multi-wavelength, multi-angle portrait of a single object, a faint speck crossing the inner solar system, watched from almost every direction we can manage.
I see it.
All of this attention produces a torrent of measurements. To turn those measurements into understanding, we have to go inside the haze of the coma and translate photons into physics. Swift's ultraviolet spectra detect hydroxyl emission when 3A Atlas is still at distances of about 3 to 3.5 astronomical units from the Sun. From the strength of that O glow, scientists infer a water production rate of roughly 40 kilograms per second, even at that relatively cold distance where solar heating is mild. That much water vapor implies an actively sublimating area of many square kilometers.
Signal locked.
Far more than a few isolated vents. Compared to typical comets observed at similar distances, 3 Atlas appears unusually active, its surface or subsurface contributing a larger fraction of its total area to outgassing. In the radio and submillimeter bands, ALMA maps the distribution of methanol, CO, and hydrogen cyanide, HCN, around the comet. The emission lines of these molecules trace a cloud of complex organics expanding away from the nucleus. As the comet approaches the Sun, methanol production increases markedly, and its abundance relative to HCN appears higher than in many solar system comets. This chemical fingerprint suggests a formation environment that is both cold and rich in certain volatiles, perhaps the outer regions of a protoplanetary disk where methanol can form efficiently on icy grained surfaces. Meanwhile, spacecraft near Mars detect signatures of water-related species as 3 Atlas passes through their fields of view, confirming that even in the thin Martian sky, the interstellar visitor's outgassing can be sensed at a distance. The combined data begin to constrain the basic properties of the nucleus itself. Hubble's high-resolution images, taken in July and again in late November, never fully resolve the solid core, but they put limits on its size. Depending on assumptions about albedo, the fraction of sunlight it reflects, and the contribution of unresolved dust, the diameter is estimated to lie somewhere between about 0.3 and 5.6 kilometers. Many analyses converge around a value near 1 kilometer, though some dynamical interpretations allow for a somewhat larger body. The truth is buried in the glare, a dark, icy fragment, a few hundred to a few thousand meters across, wrapped in a luminous envelope tens of thousands of kilometers wide. From the shape and timing of the light curve, modelers infer that localized active regions on the rotating nucleus produce collimated gas jets. These jets carry dust outward at velocities of hundreds of meters per second, dragging grains away from the surface and into the coma. As the nucleus spins, each jet sweeps through space like a rotating sprinkler, creating rotating patterns of brightness. When an active region rotates into sunlight, it flares. When it turns away, it dims. The 16.16-hour periodicity in the light curve emerges naturally from this geometry. Crucially, those same jets exert forces on the nucleus itself. Every escaping molecule carries a tiny kick. Over weeks and months, the integrated effect acts like a thruster, subtly pushing the nucleus off the purely gravitational path prescribed by Newtonian dynamics. Non-gravitational acceleration is not exotic. It is expected in active comets. But in 3A Atlas, the details of that push, and the way they intersect with the observed brightness surge near perihelion, do not fall neatly into place. Visually, the coma of 3 Atlas takes on a distinctive blue-green glow. This is not magic, but chemistry. Emission from diatomic carbon and cyanogen, energized by sunlight, superimposed on the dust-scattered continuum. The tail structure becomes complex. In addition to the main dust and ion tails streaming away from the Sun, images reveal an anti-tail, a feature that appears to point sunward, back toward the star. This is a geometry effect. Large, slow-moving dust grains, released weeks or months earlier, line up along the comet's orbit. From Earth's vantage point, looking nearly edge-on to that sheet, they can produce a narrow, sunward-pointing spike. Radiation pressure, charge interactions with the solar wind, and the viewing angle all conspire to create the illusion of a backwards tail. So far, the story is demanding but familiar. An icy body warmed by the sun, releasing gas and dust, its rotation carving patterns into the coma. its chemistry reflecting a distant birthplace. The anomalies begin when we compare all these pieces at once. As precise astrometry accumulates around perihelion, the inferred non-gravitational acceleration grows more significant. Its magnitude, and especially its direction, are not entirely straightforward to reconcile with the simplest jet models. If all the extra push came from water and other volatiles sublimating from specific patches on the surface, oriented in certain ways, we would expect a particular relationship between the brightness variations, the orientation of the tail, and the deviation from a gravitational orbit. Early fits show tensions in that relationship. The forces are real, but the exact map from observed jets to observed acceleration is still being refined. The brightness surge itself is another point of friction. As 3I Atlas nears perihelion, spacecraft coronagraphs detect a sharp increase in brightness. Not just a steady rise following the usual thermal sublimation curves. The coma becomes strongly blue-dominated, with gas emission intensifying faster than many models had projected. Some of this can be explained by enhanced activity or the sudden exposure of fresh volatiles, but the timing and amplitude of the surge still sit at the edge of what simple thermal simulations had predicted in advance. The antitail, seen in Hubble images and from ground observatories, carries its own questions. In some datasets, it looks like a classical dust sheet viewed edge-on, a thin, elongated feature aligned with the orbital plane. In others, its shape seems more teardrop-like, hints of substructure within the feature, suggesting the possibility of fragments or a swarm of smaller objects moving slightly offset from the main nucleus. Some teams interpret these features as entirely natural, arising from size-sorted dust grains and changing viewing geometry. Others leave room for the idea that 3 Atlas might be shedding sizable chunks, each with their own miniature coma. Even the size of the nucleus becomes a playground for ambiguity. The cautious bounds from Hubble and SA analyses, up to around 5 or 6 kilometers at most, compete in the public sphere with more dramatic claims, 11-kilometer diameters, Manhattan-sized comparisons, and other amplified estimates propagate through headlines much faster than corrections. This is not an anomaly in the comet itself, but a familiar artifact of the way early, uncertain measurements are translated into narrative. There are genuine compositional puzzles too. Water is detected at large solar distances, implying activity earlier than some models might expect. Methanol appears enriched, compared to many solar system comets. Some spectral hints suggest unusual nickel abundances in the dust, though those measurements sit near the edge of instrumental sensitivity. None of these observations demand new physics. All can be placed, with some stretching, into the broad diversity of known cometary behavior. But taken together, activity far out, a strong perihelion surge, non-gravitational forces that resist easy parametrization, they mark 3 Atlas as an outlier, a data point at the edge of the distribution. When data don't quite agree, theory is forced to stretch, but only as far as the evidence allows. The most conservative explanations begin with a familiar mental picture. A porous, fractal nucleus, made of ices and dust compacted just enough to hold together, riddled with voids and pockets. In such a body, heat from sunlight does not flow uniformly. It penetrates along fractures, warms isolated reservoirs of volatiles, and triggers activity in patches. As the comet rotates, these patches blink on and off. Surface layers can insulate deeper ices until they crack, collapse, or sublimate away, suddenly exposing fresh material. In this framework, the perihelion surge is the combined effect of several natural processes reaching thresholds at roughly the same time. Amorphous water ice, an irregular, glassy form formed at very low temperatures, can transform into crystalline ice when warmed, releasing trapped gases in a delayed, explosive fashion. Pockets rich in carbon monoxide or carbon dioxide, more volatile than water, can remain dormant until subsurface temperatures rise just enough to trigger rapid expansion. Surface crusts, built up over ages of gentle activity, can fail catastrophically over localized regions, dumping a sheet of dust into space and briefly boosting the coma's brightness. The antitail, in this picture, is simply that sheet. illuminated at a favorable phase angle as Earth crosses the comet's orbital plane. Large grains, less affected by radiation pressure than small ones, linger closer to the orbital path, forming an apparent spike toward the Sun. No fragments larger than boulders are required, just an ensemble of dust grains obeying the same dynamics that shape every dusty tail we have ever photographed. Chemistry adds another layer. The relatively high methanol to HCN ratio, combined with Swift's water detections, points to an origin in a cold, outer region of a protoplanetary disk where ices can preserve complex organics. Perhaps 3E Atlas formed beyond the snowlines of its home system, in a region analogous to our Kuiper Belt, but under slightly different metallicity and radiation conditions. The detailed ratios of alcohols, nitriles, and water in its coma may someday be compared to similar measurements from exoplanet atmospheres, tying together two strands of observational exoplanet science. Only after walking through these natural possibilities do some researchers allow themselves to glance toward more speculative horizons. The controversy around One Oumuamua, with its non-gravitational acceleration and unusual shape, seeded a field of ideas that has not entirely gone away. A few voices suggest that if 3I Atlas is accompanied by a swarm of fragments, those fragments might include artificial objects. Others wonder whether its non-gravitational motion could, under some reading of the data, hint at engineered propulsion, light sails, outgassing control, or other technological means. So far, nothing in the observations requires such interpretations. The forces inferred from the trajectory can be explained by outgassing within the margins of uncertainty. The brightness surge can be modeled with plausible combinations of crust failure and volatile release. No repeating narrowband signals, no geometric regularities, no clear signatures of structure appear in the data that would compel a technological hypothesis. The allure of such ideas lies partly in their narrative power and partly in the fact that, at the edges of our measurements, many profiles look similar. If the physics of 3E Atlas were ever to demand such an extraordinary explanation, the evidence would have to change. We would expect to see accelerations that cannot be made to fit any plausible gas production. We would look for reflectance spectra inconsistent with natural materials, or for dynamical behavior that indicates active control. For now, the balance of simplicity and evidence favors the natural. Exotic ices, complex thermal physics, fracture dynamics in a fragile, ancient body from another star. While theorists argue and refine, the comet itself continues its path, indifferent to our debates. From our vantage point in December 25, the next steps in its journey are already written in its orbit. But the evolution of its activity is not. The immediate milestone is its closest approach to Earth on December 19th, at about 1.8 astronomical units. That distance is large enough to guarantee safety in every conventional sense, but small enough for our most sensitive instruments to continue tracking its fading light and changing tail over the weeks and months that follow. As 3I Atlas recedes from perihelion, models of its behavior begin to diverge. In some, water production declines steadily as the surface cools, while more volatile species like carbon monoxide and carbon dioxide remain active longer, leading to a change in the relative contributions of different gases to the coma. In others, the brightness drops more abruptly, especially if the perihelion flare was driven by a transient event. A major localized collapse. A short-lived exposure of deeply buried ices that has now spent its available energy. Tracking the precise shape of the fading light curve will test these ideas. Further ahead, the March 16, 2026, encounter with Jupiter, at a distance of about 0.36 astronomical units, provides another opportunity. The changing geometry between Sun, comet, and observer will alter the appearance of the anti-tail and any lingering dust sheets along its orbit. High-precision astrometry around that time can place even tighter constraints on any remaining non-gravitational forces, refining our understanding of how its activity evolves with distance. Data will continue to arrive in delayed bursts. ASSJUICE spacecraft may downlink observations taken during windows when the comet passed through its field of view. Hubble and JWST, as long as the object remains within their brightness limits, can conduct follow-up imaging and spectroscopy, searching for changes in composition as more refractory materials dominate. Missions like TESS and SphereX, scanning the sky for other reasons, might contribute further time series and infrared snapshots, filling in gaps in the timeline. Each of these future observations is not just another point on a graph. They are tests. If brightness declines slowly and non-gravitational forces persist at a measurable level, that will favor models with extended activity from deep volatiles. If the comet's acceleration falls away faster than expected, or if the anti-tail geometry changes in surprising ways, that will suggest different internal structures and histories. The months ahead become a kind of global, distributed experiment. An entire planet of instruments watching one fragment of another star system as it leaves. Eventually, though, the signal will slip below our thresholds. The heartbeat will disappear into the noise. When that happens, what remains? We are left with an object that arrived unannounced, flared in a way we did not fully anticipate, and then vanished into interstellar night. Its unexplained brightness surge is not a failure of science, but a reminder of scale. Even in an era of precision photometry and high-resolution spectroscopy, nature still finds ways to arrange familiar ingredients into unfamiliar patterns. In the chemistry of 3A Atlas, we glimpse something profound. Water, methanol, hydrogen cyanide, and other volatiles drifting away from its nucleus are not exotic substances. They are the same building blocks we see in star-forming regions, in protoplanetary disks, in the comets of our own system. Their presence here, in an object that demonstrably formed around another star, reinforces a quiet conclusion. The raw materials for life are not confined to one corner of the galaxy. They are widespread, written into the basic physics of cooling gas and dust. This does not mean 3 Atlas carries life. There is at present no direct evidence of biology in its spectra, no signs of complex macromolecules, no patterns in its behavior that would indicate metabolism or design. Yet it does occupy a place in broader discussions. Some researchers invoke interstellar comets when they think about panspermia, the idea that life, or its precursors, might travel between systems. Others use objects like 3E Atlas as test cases in debates about how we would recognize engineered artifacts, if they ever crossed our sky. What the comet gives us, concretely, is chemistry and dynamics, not answers. Its nucleus size is still bounded by uncertainties measured in kilometers. Its outgassing history is reconstructed from fits that carry assumptions and degeneracies. Non-gravitational terms in its orbit solution encode physical processes we do not yet model in full detail. The gap between what we can observe, a small patch of pixels, a handful of spectral lines, a fit to positional residuals, and the true complexity of a multi-kilometer body is wide. In that gap lies scientific humility. 3I Atlas is a reminder that, even close to home, our picture of reality is built from sparse data and models that are always provisional. Our instruments are extraordinary, capable of seeing a frozen fragment from another star system, millions of kilometers away. But the universe is not obliged to be simple. Somewhere, far back along its trajectory, this object orbited a different sun. It may have spent hundreds of millions of years in a distant comet cloud, perturbed now and then by passing stars. A gradual nudge, a rare close encounter, or a rearrangement of giant planets in that unknown system eventually gave it escape velocity. From that moment on, it traveled in darkness, feeling only the weak pull of the galactic potential, carrying within it a record of temperature histories, irradiation, and chemistry spanning epochs. For most of that time, no one watched. No one knew it existed. For a brief interval measured in months, it became one of the most carefully studied objects in our sky. Our telescopes turned, our detectors cooled, our software pipelines adjusted for its motion. Then, inevitably, it faded back into anonymity, joining the vast population of unseen interstellar fragments that must wander between stars. It is tempting to imagine that many such messengers pass through our solar system unnoticed, smaller or darker than 3I Atlas, their signals buried beneath the brightness limits of our surveys. Each would carry a slightly different version of planetary history, different ratios of methanol to water, different abundances of complex organics, different fracture patterns and porosities, all encoding the physics of their birthplaces. Together, They form an invisible census of planetary system architectures scattered across the Milky Way. We are at the beginning of learning to listen to them. For now, we have glimpsed only 3 with certainty. As 3I Atlas recedes into the outer darkness, its light curve shrinking toward 0, we are left with a set of unresolved threads. A brightness surge that strains our models, a non-gravitational acceleration that invites more refined fits, an antitail whose fine structure may or may not whisper of fragments. None of these are proof of anything beyond the reach of natural comet science. All of them are invitations to observe more carefully, to model more deeply, to accept that even familiar physics can produce unfamiliar behavior when applied to matter shaped under other suns. In the end, the deepest impression may not be the anomaly itself, but the timing. An object that has traveled between stars for longer than our species has intersected our instruments at just this moment in our technological history. We were able to see its heartbeat, to measure the faint push of its outgassing, to parse its chemistry into lines and ratios. For a brief time, it became part of our story. Then it moved on, indifferent, carrying its unanswered questions into the dark.